This video will cover chapter 2, section 1 to 4. Okay. To chapter 2, we're going to talk about the graphs of functions, somehow going back to functions. Then first and second derivative rules for second derivative tests on curve sketching. So it means we're going to use first derivative and second derivative to sketch the graph of a function. More about sketching the graph. All right. So this is a polynomial function, right? This is one piece of string. And when we talk about functions, we like to talk about increasing and decreasing. You see, this function is an increasing function. From left to right, we see a little bit, it keeps increasing. Right? Well, let's see this ones. We see this one, first one, A, is an increasing function. It just keeps from left to right, just keeps going up, keeps going up. So increasing function. Well, let's see B. Increasing until this point. Until this point. This point we actually call max. Because you see this point has a maximum function value or the y value. Because all other points are lowered. So we call this point maximum. Then from this point, we see it decreasing, the function started decreasing. We always talk about from left to right. All right, so this one C, we see the function decreasing, decreasing, decreasing until this point, there's a turning point, right? So this C is a turning point. Here, this point is a turning point. Until a turning point, the function goes up, right? Become increasing. D is a decreasing, right? Keeps decreasing, keeps decreasing, keeps going down, keeps going down, keeps going down. E, increasing, 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 increasing. A little bit almost flat, but still increasing, right? So extreme points, talk about the maximum point and minimum point. We see in these two graphs, we have downward parabola. In this case, we call this one maximum. Upward parabola, we call this one minimum. So maximum, minimum could be local maximum, local minimum, or relative maximum, relative minimum, which means in the period, in the interval. Absolute means throughout the domain, throughout the domain. Let's see those points. Okay. So the first one, the first function, the domain is from 0 up to 5. Right? 0 up to 5, the x value. So let's see what happens in this one. We see this point, then we see this point, we see this point, we see this point, we see this point. So how do we analyze those points? It really depends on which interval we're talking about, right? If we talk about the whole domain, well, 2, 5, this would be maximum, absolute maximum. And 4, 1 will be absolute minimum, right? Absolute. But we can also talk about local or relative, right? Sometimes we don't refer to the whole domain. We can refer to a interval, right? Let's see, this value is 1. We can talk about from 0 to 1. Well, this point is local or relative maximum, and this point is relative or local minimum. So that's just the terms of absolute and relative. Okay, another one term is called concavity. What does that mean? Let's see these two functions, right? Both functions are decreasing. This function decreases, and this function decreases, but they decrease differently, right? We see this is concave down. We call this a concave down. It's like a cup, right? Imagine this is half of the cup down. This is a cup up or concave up. Right? So concave up, concave down. And so we have names for this. So if we have a graph goes like this, at this point, and this point, we call we call turning point, critical point, critical, right? A turn function goes increasing to decreasing, or from decreasing to increasing. We call critical points. So that's the name for those two. But when we change from concave up, you see this is concave up. After this point, it becomes concave down. We call inflection point. We call those points this point, this point, this point, called the inflection point, right? The critical point is when the function derivative equals to 0. The inflection point we can find from setting the second derivative to be 0. So that's what happens with these points. So those inflection points cause the second derivative function to be 0. And these critical points cause the first derivative function to be 0. So let's see this one. So I want to describe this function. Okay. So there are a couple of functions, a couple of questions. I don't see the question. I only see the solution. That's interesting. Oh, okay. Let's just go through these ideas. So for x less than 3, where is x less than 3? From here, right? Starting from 3, not including 3, because there's no equal sign. So x less than 3, all those values. What happens to a function? F of x is increasing and concave down. Imagine this negative infinity somewhere here. This is a function from negative infinity up to 3 is an increasing function and is concave down. So relative maximum point at x equals 3. How do we know? Because this one is a horizontal line, right? Horizontal lines is a constant. It's constant. So the slope of this tangent line, so the tangent line is a horizontal line. The slope of this tangent line equals 0. Right? Remember this line is y equals 5. Right? No x does not depend on x, it's a constant function. So the derivative is 0. And also same thing for this point. The tangent line is a horizontal line. So the derivative we can write like this. 5 equals 0. And what's this value? This value is 3. Right? So derivative at 3 is 0, derivative at 5 is 0. So that's why we know that's relative maximum. Because the derivative is 0. The highest point in this, the tangent line is horizontal line. Same thing for the minimum. The tangent line is horizontal line. So slope is 0. That means the derivative of the function at this point is 0. In between 3 and 4, what happens? In between 3 and 4, the function decreases and concave down, right? Function decreasing and concave down. Then x equal to 4, is the inflection point, right? Change from concave up. No, this is wrong. This is typo. This is not the inflection point. It's a critical point. Right? Remember, inflection point changes concave up to concave down. So this kind of point is called inflection point. But this one, you see the concave up, concave up, concave up. On both sides of x, oh, this is 5. I'm looking at the wrong point. So this is right. I'm looking at the wrong spot. You see x equals 4 is here, right? It is inflection point. It changes the concave down to concave up. But x equals 5, so those 2 points are critical points. X equals 4 is an inflection point. From 4 to 5, what happens? From 4 to 5 is concave up, but a decreasing function. And the relative minimum at 5, right? Critical point. For x greater than 5, function for x greater than 5 from this moment on is concave up and increasing. Intercepts, undefined points, and asymptotes. So polynomial function is one piece of string, right? There's no breaking point, there's no asymptotes. But here we see y-axis, or we call x equals to 0. That's the name of y-axis in two-dimensional world. Is not asymptote, right? So because x can never be 0. So what happens when x approaches to 0 from the left-hand side? The function value goes to negative infinity. On the right-hand side, it goes up to positive infinity. But this function, x cannot be negative, so x do not go to the left-hand side. And these 3 functions, we see this function approaches to this line, but will never touch this line. So this line is called horizontal asymptotes. Horizontal asymptotes. This one is also horizontal asymptotes. This is called a slant asymptotes. Okay, earlier we see the x equals 0, the vertical asymptote. Yeah, those are vertical asymptotes. So how do we describe a function, a graph of a function? We can talk about the intervals in which the function is increasing or decreasing, talk about the relative maximum points, relative minimum points, those critical points. We can talk about the maximum value, minimum value means the function value. We can talk about the intervals in which function is concave up or concave down, talk about the inflection points. We can talk about x-intercept, y-intercept, or undefined points. Undefined points, usually we see open circle. The asymptotes. So when we graph a function, we can involve all those characteristics, or we can use these characteristics to sketch a graph of a function. Okay, that's one. section 1. Let's see section 2, how do we use first derivative and second derivative? Right, first derivative, we use f prime of x. Second derivative, we see f double prime of x. So the first derivative, right, at a point is the slope of the tangent line. So this is a picture of a first slope. What is the rate of change of this function at this point? Right. So f prime of a equals to the slope of this tangent line. Well, same thing for this one, right? So this one, the first one concave up, the second one concave up, both concave up. So if the first derivative is positive, then function f is increasing. You see this first one, concave up, the function is increasing. How do we know? Because slope of this tangent line is positive. And this one function is decreasing, the slope is negative. Slope of this tangent line is negative. Let's see this example. This example given 1 point, right? X equals 3, y equals 4. So 3, 4 as a point. Then this is saying when x greater than 3, the slope is positive. Function increases. Right? At 3 equals 0. This is an extreme point or critical point. Less than 0 when x less than 3 decreases. Right? Original function decreases. So have this 3, 4 point. Then at this point, because of this condition, so we know this is extreme point. On the left-hand side of 3, so this is 3. On the left-hand side means the value is less than 3. Because the derivative is positive, so that means the function increases. We don't know how, but somehow like this increases. So the function increases. Then on the right-hand side, the function decreases because the derivative is negative. Something like this. Well, let's see second derivative. Oops. What did I do? Okay, if the second derivative is positive, then we know the graph concave up. If second derivative is negative, then it's concave down. Okay. If the second derivative equals 0, that gives us the inflection point. Let's see this one, this table. So the first derivative is positive because the original function increases. The second derivative is positive because it's concave up. First derivative positive because the function increases. Second derivative is negative because it's concave down. First derivative negative because it decreases. Second derivative positive because it's concave up. First derivative negative because the original function decreases. Second derivative is negative because it's concave down. Now let's see this one. So this one we're given 3 points, right? 2, 3, 4, 5, 6, 7 on the graph. Then the first derivative at 6 equals 0, so that gives us a critical point. And at 2 equals 0, so we get 2 critical points. When x value equals 6, when x value equals to 2. So then second derivative positive for x less than 4. At 4 equals 0, right? So that means that we're given 2 critical points and 1 inflection point. Second derivative negative when x becomes greater than 4. So now let's graph those 3 points. Once we have 3 points, we're looking for f of 6. So f of 6 is right here at the third point. F of 6 and f prime of 2. So that means this point is a critical. This point is a critical point, and this point is a critical point. And it seems like this 2, 3 is minimum, 6, 7 is maximum. Then the second derivative is concave up for x less than 4. So on the left-hand side is concave up. So we know the graph goes concave up, goes this way, concave up. On the right-hand side is concave down. On the right-hand side, concave down. So we know, oh, I somehow I draw the opposite. So note this is concave up. Concave up. On the right-hand side is concave down. Right, like this. That's how we use first derivative and second derivative to sketch the graph. Not exact, but also we're given these 2 points as critical point, right? So we know this is a critical point, this is a critical point, and we know this is concave up, concave down, right? Once this concave down, that goes like that. So between original function and first derivative, well, derivative is positive, increases, right? Derivative is negative, decreases. So this is a polynomial of 3, right? Because the x raised by 3. We see the function increases and the concave down. The function still increases, but the concave up. So the function decreases and the concave down. Let's go through this one. We're saying, what is the slope of the graph when x equals 1? Well, that's x equals 1 right here, right? So the slope is, what is this? Is this one? Right? Is this the slope of this tangent line? The derivative change in the interval from 1 to 2. So from 1 to 2, how is the first derivative change? Right. Imagine, let's draw some pictures. Imagine from 1 to 2, right? The tangent line here is like this. The tangent line here is like this. Oops, like this. The tangent line here is like this. It's not very obvious, but we could see the slopes become smaller and smaller. All right, I don't like this question, actually. It's not obvious. All right, so that's section 2 basically tell us what's the relationship between first derivative. So let's make this. We have original function, we have first derivative, and we have second derivative, right? So what is the relation? So if the original function increases, the first derivative is greater than 0, but we cannot tell about the second derivative. If the original function decreases, we know the first derivative is less than 0. We cannot tell about the second derivative. The second derivative is telling by the concave up or down, right? If it's concave up, the second derivative is positive. If it's concave down, the second derivative is negative. So that is a relation. Okay, the first derivative and second derivative test. Let's review those graphs again. Right. So we have critical point here. Right. At this point, derivative equals to 0. And the function increases at the left-hand side, we know the first derivative positive. The function decreases on the right-hand side, so the first derivative negative. And we have a minimum point here at this point. So I should say this is f prime of A. So f prime of A equals 0 critical point. On the left-hand side, the function decreases, so the derivative is less than 0, negative. On the right-hand side, function increases, so the first derivative positive. Let's see this one. The function increases and the concave down, right? So the first derivative is positive, but second derivative negative, right? Because it's concave down. So after this inflection point, it becomes concave up. So it's still increasing because the function increases here, increases everywhere. But the second derivative after A, on the right-hand side of A, is positive, right? Concave down, change to concave up. This is concave up, change to concave down. It's opposite. Okay, let's see this one. We want to find the local maximum, local minimum points. Or maybe let's do one more step. Let's find also, so local maximum and local minimum are given by critical points. Let's also find concave up, concave down. Concave up, concave down. That's by finding inflection points, right? So local maximum, so maximum or minimum, we find by taking derivative of the function, we set to 0, then we solve for x. So let's take a derivative of this function. So 1/3 times 3, that's 1. So we get x squared minus 4x plus 3. And then we set this one to be 0. And this we can factor out. X minus 1, x minus 3. So by 0 property, you can split the two factors. So we solve this, we get x equals 1, x equals to 3. Because we're looking for the points, so we need to plug back in f of 1 to find the function value. Well, x equals 1, that's just equal to 1/3 minus 2 plus 3 plus 1. We just substitute 1 into the original function, right? So 3 plus 1, 4, 4 minus 2, 2, and 2 and 1/3, so that's 7/3. Then we evaluate f of 3. So 1/3 times 3 cubed minus 2 times 3 squared plus 3 times 3 plus 1. Well, 1 dirt times 3 is 1, so I have 3 squared, which is 9. Well, 3 squared 9 times 2, 18. 3 times 3, 9 again, plus 1. So 9 plus 9, 18. 18 minus 18, 0, so we just get 1. So we get 2 points, right? So we get 2 points. We get 1, comma, 7 over 3, and 3, comma, 1. We have these 2 points. Now, let's see concave up, concave down. Actually, this is polynomial degree 3, and the coefficient is positive. So we know the behavior looks like this. The behavior like this. All right, so finding concave up, concave down, we set the second derivative, right? So this is the first derivative. We have this first derivative. Now we take a derivative of this function, not setting equal to 0, treating this function. So we find the second derivative. We take a derivative to the first derivative, so get 2x minus 4. Then we set this one to be 0. So we divide by 2 on both sides. So there's a 2 times x minus 2 equals 0. We divide by 2, we get x minus 2 equals 0. So x equals 2. Then we evaluate f of 2. That's 1 third times 2 raised by 3 minus 2 times 2 squared plus 3 times 2 plus 1. I just plug back into the function. So 2 raised by 3, that's 8. So that's 8 divided by 3. Then minus 2 squared 4, 4 times negative 2, negative 8. Then plus 6 plus 1, that's plus 7. Right? So 8, I can, so 8 divided by 3. Right, 8 divided by 3, just 2 third, right? Then minus 8 plus 7, just minus 1. Well, 2 minus 1 is 1. So 1, which is 5 over 3. Yeah. So I got a 2, comma, 5 over 3 as the critical point, right? So which means, so the graph, my graph looks bad. So let me regraph it. So the graph looks like I do have a inflection point, which is 2 comma 5 over 3. You see red in between of those two, 2 comma 5 over 3. And on this side, let me see, how do I do this? Yeah. No, wrong way to draw this. I'm horrible at drawing. I'm horrible at drawing. So it should be, you know what? I'm horrible at drawing. So let's just see the graph from the textbook, because I don't want to misleading you. Okay, it's like this. All right. So how do we find? So once we have 3 points, right? We have 1, we have 2, we have 3, but this one only did with 1 and 1 between 3 and 3. Remember, we have 2 critical points. Right? We solve for 2 critical points. So x equals 1 and 3, the 2 critical points. So we split the interval into these kind of intervals. So x less than 1, right? So this is for x equals 1, x equals 3. And in between, x in between 1 and 3, and x is greater than 3. So what happens? How the graph behaves. So we can just pick one value. We just pick one value because we only know those 2 extreme points, right? Critical points. We don't know which one is maximum. We don't know which one is minimum. So all we have to do is pick one value. Let's see. Pick a value on the left-hand side of 1. Well, easy, 0. Then to plug in to get what's f of 0. what's f prime of 0? Then, according to this, it's positive, right? Because I already delete. Right? This is positive, so that means the original function increases. Then in between of this, we can just pick 2. Then we evaluate f prime of 2 to see if it's positive or negative. If it's positive, function increases. If it's negative, function decreases. But since we already know 1 is a critical point, it turns the increasing to decreasing. So actually, as long as we figure out the first one, the rest just come along. The rest just come along. That's a beautiful thing for polynomial function, right? We have figured out this one. We figure out we have 2 critical points, x equals 1, x equals 3. And we evaluate f prime of 0, which is positive. And then we know the function in this interval from -infinity up to 1 increases. So because 1 is the relative minimum or the extreme, the critical points, so we know on the other side has to be the opposite. Right? Also, this one has to be opposite. And then we see clearly 2 here, x1, x equals 2, it turns the cup down to cup up. Okay, let's see this one. Again, a similar question, right? We want to find the local maximum and local minimum. So which means we want to take a derivative of this function, then we set to be 0 to solve for x. While taking derivative of this, remember we have to use the chain rule. So first we have to deal with this layer. Right? We take 3 down, we keep the inside, whatever the inside is, 3 minus 1, now raised by square. Then we multiply by the derivative of inside, which is 3. 3 times 3, 9. 3x minus 1 squared. Then we set this one to be 0. Well, then we divide by 9 on both sides, so get 3x minus 1 to be 0, squared to be 0. That means 3x minus 1 has to be 0. So which means x equals 1/3. So we solve x for 1/3, then we plug in to find the function value, which is 0. Because 3 times 1/3 is 1, 1 minus 1 is 0. So 3, 1, 0 is the only critical point. So 3, 1, 0 is the only critical point, right? If we use our calculator to graph it, we get a picture of this. We see 1/3 is a critical point, also an inflection point, because it also turns the graph from downward to upward, right? Concave down to concave up. So let's see the second derivative test. So once we find a critical point, if the second derivative is less than 0, then f is a local maximum. What is second derivative less than 0? Second derivative less than 0 means it's a concave down, right? Concave down. If it's concave down, it has to be maximum. And if we find a critical point and it's concave up, it has to be local minimum. It's very intuitive. So let's see this one. So the graph of this quadratic function is a parabola, is upward parabola, right? Because you see the number before x squared is positive. It has one relative extreme point. So find it and sketch it. So when you take the first derivative, right? Oh, actually we did already here. But take derivative, so get a 1/4 times 2, which is a half, then x raised by 1, then minus 1. Right? The second derivative is just half. You see this is a polynomial degree 2, polynomial degree 1, polynomial degree 0. So you see the degree decreases one at a time at one level of derivative. So that's a pattern when we take derivatives of a function. Then once we have that, we can find the value, right? Then we can plug in the critical point. Then we can check the interval, right? What's on the left-hand side, on the right-hand side. Once we check, you see on the left-hand side, the function decreases. On the right-hand side, function increases. So we can sketch. Sketch means, not exact. We just give the, visual picture of it. Not exact cover all the points needed. So this one is similar polynomial degree 3. We take first derivative, take second derivative. Right? First level, we see polynomial degree 2. Third level, polynomial degree 1 or linear. Right? So each level of derivative just lower the degree one time. Then we do the same thing. We look at the two critical points. Then we check certain values in the interval. Then we can use the second derivative test. Right? Then we can graph. Okay, another one is locating inflection points. We set a second derivative to be 0. Let's see this one. How do we find the inflection points? Which means we need to find the second derivative of the function, then set it to be 0, then solve for x. So the first derivative is 3x squared minus 6x. That's it. The second derivative is we're taking the derivative of the first derivative. 3 times 2, 6. X minus 6. Then we set this one to be 0. We divide by 6, we get x. So we get x equals 1. Then we plug in to the original function to get a function value. So we get 1, 3 as the inflection point. If we graph it, we see this. Right? So 1, 3 is the inflection point. You're turning the concave down to concave up. This one is similar. All right, so we want to sketch it. How do we sketch? First, we find the critical points, then we find the inflection points. Then we evaluate a value on the left-hand side, on the right-hand side. Then we can graph them. All right. Okay, that's section 3 about the graphs of the derivatives. So section 4, putting everything together. See, if it's a quadratic, we need to solve for a quadratic formula. We use quadratic formula to solve for quadratic equations. Let's see the first one. We want to sketch this. We want to find the first derivative and second derivative. Where first derivative is x minus 4. Second derivative is a constant. So which means we have no inflection point. We only have a critical point. What's critical point? We set this one to be 0, so x equals to 4. Once x equals to 4, we can find f of 4, which is negative 1. So that will be our critical point, but we don't have inflection point. Also, we want to find x-intercepts. X-intercept will set the function to be 0, right? Because the y value is 0. Then we solve for x. And also, the y-intercept is easy. Y-intercept is just 0, 7. Then we can graph. We have 0, 7. We have a 4, negative 1 as the vertex, the minimum point. Then we have solved the two irrational roots. And that's it. We put those points on the graph. Polynomial 3, degree 3, is similar. Solve for the first derivative, set to be 0. We solve for critical points. We have 3 critical points here. Yeah. Oh, no, we have 2. We have two critical points because this is a quadratic equation. Okay? We have two values. If we solve it, first, okay, let's solve it from here because I don't see it. So we take a derivative set to be 0. Now we have this half. So what we need to get rid of this half. So we multiply everybody with 2. Right? Then we have x squared minus 6x plus 10 equals 0. Then we want to factor this. So we need to think about two numbers add together to be, okay, it's not factorable. So we have to use quadratic formula. We have to use quadratic formula. Okay, also can set the second derivative to be 0. Second derivative is just this x minus 3. When we set to be 0, get 3. So 3 is an inflection number. Then we can evaluate x equals 3 for the original function, we get 7. So 3 comma 7 is the inflection point. So we only have this one x-intercept. So this 3 comma 7 is the inflection point. You can also think about this graph in the sense of algebra, right? This is a polynomial degree 3. The leading coefficient is positive, so the graph has to go this way, the n behavior. Okay, let's see this one. We want to sketch this graph using the derivative test. We need to solve for first derivative, then set to be 0, so get x equals 2. Second derivative, we need to set to be 0, also 2. So in this case, x equals 2 is the point of, it's the inflection point, also critical point. Okay, so we solve it, so the y-intercept is obvious, right? That's the setting x to be 0, then the function value is 15. So we have this y-intercept. Then for x-intercept, we set the function to be 0, then we solve it. So we'll get a 3 and 1, two values. So we get 3 comma 0, 1 comma 0 as 2 x-intercepts. So I have some picture like this. 1 cause function to be 0, 3 cause function to be 0. And when x is 0, the function value is 15. So that's y-intercept. If a rational function involves, we'll see asymptotes. We'll see these slant asymptotes. All right, so for us, we need to know the simple one, like before. And so how do we graph? So given f of x, so first step, we need to find f prime of x set to be 0, find the critical points. 2, we find the second derivative, we set to be 0, we find the inflection points. So once we have these points, we just evaluate, so we will have, let's see, critical points, it depends on how many we have, right? We will have intervals. So the first critical point, second critical point, maybe you have more for higher degree. Then that divides into intervals. So we have to evaluate, we have to pick any value in this. Let's call this 8, to see if it's a positive or to see if it's a negative. If it's positive, that means the original function increases. If it's a negative, original function decreases. Then for the second one, also we evaluate. If it's positive, it's a concave up. If it's negative, it's a concave down. So we'll use this kind of to graph. And of course, we can find x-intercept by setting the function to be 0. We can find a y-intercept by setting x to be 0. All right, that's how we graph. That's how we sketch a function. Okay, that covers 1 through 4. Okay.